color guard is a part of marching band, greatly the visual aspect of a field show. The color guard spins flags, rifles, and other props in a combination of dance and marching.
A typical flag weighs 2.01 pounds and is 186.4 centimeters from end cap to end cap.
A typical rifle weighs around 2.8 pounds and is 90.8 centimeters long. The first measurement we found was the center of mass of the flag, which we did by taking the flag and placing our fingers at opposite ends until they met at the center and equally balanced the flag on either side. The center of mass was almost exactly on the tab, which is the tape connecting the silk to the pole.
We then repeated this process on a pole without a silk and found the center of mass to be 4.1 centimeters below where the tab would have been. To find the net torque, we use the equation torque equals radius times force of gravity, with the force of gravity being the object's weight.
To find the radius, we measured the length of the flag and divided by 2 to find the midpoint of the flag, which was 93.2 centimeters. Because of the weights in the top and bottom of the flag, the midpoint was not the center of the mass. We used the difference between the midpoint and the center of mass to find the radius to be 4.1 centimeters, which we converted into 0.041 meters because torque is measured in Newton meters.
Cool. Okay.
To find the flag's weight, we weighed Hannah, then we weighed Hannah while she was holding the flag. We then subtracted her original weight from this value, then converted it into newtons. The flag weighed approximately 2 pounds, and we know that 1 pound equals 4.45 newtons, so we multiplied the weight of the flag by 4.45 to find the force of gravity on the flag. We then multiplied the radius and the force of gravity to find the torque to be 0.36 newton meters.
The moment of inertia is a quantity expressing a body's tendency to resist angular acceleration.
To find the moment of inertia, we use the equation mass times radius squared.
In this situation, the radius was the length of the rifle from where Emily tossed it.
We found the mass of the rifle to be 1.27 kilograms, then multiplied it by the length from the bottom of the rifle to where Emily tossed it from.
When she did a butt toss, which is a toss from the tip of the rifle, the radius value was 0.0908 meters, the entire length of the rifle.
When she tossed the rifle the standard way, from closer to the center of the rifle, the value we used for the radius was 0.379 meters.
We then multiplied the squares of these values times the mass of the rifle, and found the moment of inertia for the butt toss to be 0.0105 kilogram square meters, and 0.0018 kilogram square meters for the regular toss.
We repeated this test using a flag as well. Hannah did a silk toss, which is tossed from halfway between the tab and the end cap, and a pop toss, which is tossed from the tab.
The mass of the flag was 0.908 kilograms, so we multiplied that times the length of the tip of the flag to the tab, 0.935 meters, to be the radius of the pop toss. To find the radius of the silk toss, we measured the distance from the tip to the point of Hannah's release, 1.35 meters.
After applying the same formula we used for the rifle, we found the moment of inertia for the pop toss to be 0.79 kilogram square meters, and the moment of inertia for the silk toss to be 1.7 kilogram square meters.
The silk toss's moment of inertia was so much greater because the radius was bigger, so Hannah created a bigger circle in the air than she did with the pop toss.
This also applies to the rifle tosses demonstrated by Emily, where the butt toss's radius was bigger than that of a regular toss.
To express circular motion, Hannah did drop spins, the first basic skill anyone learns in Colorguard.
We found the average time it took her to do each drop spin by taking data from 4 drop spins and averaging them out to be 1.58 seconds with a margin of error to be plus or minus 0.1 seconds.
Next, we found the circumference of the circle the flag made by multiplying the diameter times pi. We then divided the circumference value by 1.58 to find a rate of 1.85 meters per second for each drop spin. The guard gets around primarily by jazz running or jazz walking. Jazz running and walking are the act of pointing all the way through your leg as you place your foot on the ground, toes first.
To find the work done while jazz running, we timed Hannah for 3 seconds to see how far she could get. Then we measured the distance.
We found her acceleration by subtracting the initial velocity, which was 0 because she was at rest, from the final velocity, which we found by measuring her distance over the 3 seconds. We found that her final velocity minus her initial velocity divided by 3 seconds was 1.1 meters per second squared.
With this acceleration, we were able to find her force after converting Hannah's weight into kilograms and multiplying her mass times her acceleration. Her force was 60.83 newtons.
Finally, we found the work she did by multiplying her force times her displacement, 9.8 meters, to find 596 joules as her final work.
We repeated this process for jazz walking as well.
Because her displacement was less than that when she was jazz running, she did much less work walking. Her total displacement was 3.66 meters.
Using the same equations, we found her total applied force while walking to be 22.67 newtons and the work to be 83.0 joules.
From the work, we found the power it takes for Hannah to jazz run and jazz walk. For jazz running, we took the work over the time and found it to be 199 watts. For walking, we found the power to be 27.6 watts.
The power and work for jazz running were much greater than that of jazz walking because she covered a greater distance in the same amount of time.
Clearly, Colorguard takes a lot of effort, skill, and work. Marching band as a whole is a sport that requires dedication and grace, and Colorguard is a major aspect of it.